All right, everybody, we are on this page. I know I think some people might have a different packet, but we're on section 4.4, Descartes' rule of signs and rational zeros. So the next couple of classes we're going to be spent looking at this complete factorization process. So basically, when we have a polynomial, we know it can be written as a product of its linear factors with a linear a product of its linear factors with a leading coefficient. So really what that tells us is we can take a polynomial in standard form, x to the fourth plus 2x third, et cetera, we can turn that into a factored version. So it might be like x minus 2, x plus 1. How about this, like x minus 2 plus I, and x minus 2 minus I, et cetera, et cetera, et cetera. And there might be a leading coefficient in front of it that makes it fit the correct end behavior and the correct y-intercept. So that's what we're going to really dive into the next couple classes. So we're going to start this process by just defining this complete factorization theorem. It's really what I just said. So if we have a polynomial function where the degree of n is greater than 1, so we're not talking about that constant, so f of x equals 2, where we thought about, well, is it a polynomial or not? And we kind of said, well, it kind of is because it's x to the 0 power. For these to happen, there has to be a degree greater than 1. Then there exists n roots or numbers, real or complex, such that we can turn this polynomial into its factored form. So really what I just said. You should have as many factors as the degree of p of x. So if it's a fifth degree, you should have 5 factors. There could be complex roots, there could be irrational roots, there could be multiplicities. So make a little mental note of that. That's going to come into play. But we should have as many factors as the degree. All right, and that's again reiterating what I just said. The zeros theorem, every polynomial of n greater than 1 has exactly n zeros, provided that a multiplicity is counted however many times it happens. So x squared still has 2 zeros, but the root 0 is counted twice. All right, so nothing new there. So we look at this function, p of x equals x to the third minus 4x squared plus 3x minus 8. We try to do a little bit of work with it. Can I factor something out? Is it a factor by grouping? Unfortunately not. So we have other options. And this complete factorization process, I know I have them labeled in steps. You don't really need to think about it in terms of steps. We just want to think about it as what we need to do to go from the beginning to the end of this process. So step one isn't necessary, but it's going to be a help when we start digging into some more complex polynomials. It's going to give us a little idea of where to start. It's one piece of the puzzle. So we're going to use this Descartes theorem to figure out the possible number of real zeros. All right, and real is the key word there. Real basically means not imaginary. So real could be rational or irrational. So, it could be a quadratic formula situation. But Descartes' rule of signs says let p be a polynomial function with real coefficients. The number of positive real zeros, x equals 4, x equals 1/2, x equals 2 plus radical 3. Those are all real zeros. It's either equal to the number of variations in sign or less than that by an even whole number. So you're going to do a couple of these, and that's a lot of words, and it seems confusing. You're going to get the hang of it pretty quick. So really what that says is if there are 4 sign changes in our polynomial. So if it goes from x to the fourth, and then minus x to the third, plus x squared, basically if it's changing signs, minus to a positive, plus or minus, if it's changing signs 4 times, that means there's either 4, and then less than that by an even whole number, 4, 2, or 0 real positive roots. All right, so if there's 4 sign changes, there could be 4, 2, or 0 real positive roots. Let's say there's 3 sign changes in my polynomial. That means there could be at most 3 or 1 real positive root. So basically it's the number of sign changes and you just take away 2 from each of them. So that's super important. So you can kind of think about this now. We're going to talk about this next class, but why do I have to take away 2 from that? Why does it go from 4 to 2? So if there's 4 roots, four sign changes, 4 positive roots, why does it have to jump down from 4 to 2? Why can't there be 4, 3, 2, 1, or 0? So think about that. And then we can do the same thing to find the number of negative real roots of a polynomial. It's the same thing. It's the number of changes in sign. But we have to evaluate p of negative x to find out the number of negative real roots. So like I said, we'll do an example or two, and once we do that, it's a lot to look at, but it's not that bad. So here's p of x, x to the third minus 4x squared plus 3x plus 8. Looking at that polynomial, we don't have any strategies right now to factor it. But what we can do is we can narrow it down. We can think about how many positive roots there could be and how many negative real roots there can be. So we look at the sign changes. It goes from a positive x cubed to a negative 4x squared. That's one sign change. It goes from a negative to a positive. There's my second sign change, and then it stays positive all the way to the end. So for p of x, there's 2 sign changes. That means there could be 2 or 0 real positive roots. Now we do p of negative x. All right, so negative x to the third. You don't need to show this every time. You're going to get the hang of finding the pattern here. Minus 4 times negative x squared plus 3 times negative x plus 8. So basically the short version is whenever there's an odd power, the sign changes, right? Negative times negative x is negative x cubed. Negative x squared is positive, so the sign doesn't change here. Okay, so if it's an odd power, the sign changes. Oops, that 2 should have been out here, my bad. If it's even, the sign doesn't change. All right, and then we have minus 3x plus 8. So we kind of already know what's going to happen here in this case. We know we have a third degree polynomial, so there should be 3 roots that show up. So let's look at our sign changes. We start negative, we stay negative, we stay negative. There's my first and only sign change. So we know there is 1 real negative root. All right, so here's why this is kind of interesting. We have options here, right? There could be 2 positive and 1 negative. So we could have this combination. There's my 3 roots, 2 positive real, 1 negative real. So x could be x equals 2, x equals 4, x equals negative 1. But let's say it's the other case. Let's say it's 0 real positive and 1 real negative. So hopefully you're kind of seeing why it has to go down by an even number. If it's 0 real positive and 1 real negative, that's only 1 root. So I want you to think about for next time, where are the other 2? So where could those other 2 roots be? Because we know they have to have 3, but if I only have 0 real and 0 positive and 1 negative, where are those other 2 roots? Okay, so we're going to get plenty of time to practice this in class. I'm going to pause the video and show my work for the next example there. So if you want to try that one out and check my work, you can. And then we'll move on. So if you haven't, go ahead and pause now. Okay, so there's my answer for that one. And again, you see the puzzle fits. 3 potential real positive, 2 potential real negative. That gives me my 5 total. We could also have any other combination. I could have 1 real positive and 2 real negative. I could have 1 real positive and 0 real negative. So I can only have 1 real root. So the question again is, where are the other 4? Okay, so that's how we're going to use Descartes' rule to kind of give us an idea of what the roots are, what the nature of the roots are. Okay, so we'll practice in class. Don't worry about this one. This kind of spilled over the next page. We can look at that later. You can do it if you want. So Descartes' rule can help us find the number of possible real roots. The number of possible real roots. But it doesn't tell us what they are. So we've narrowed it down a little bit. We know positive and negative, but we don't know what the heck the roots are, what we should be trying. So the rational zeros theorem is the next thing we're going to do in this process. So if a polynomial p of x is written in standard form and has integer coefficients, then every rational, again, rational, not quadratic formula, not radicals, rational zeros is in the form p over q, where p is a factor of the constant. So I jotted a little easy example here. That would be the p, and q are the factors of the leading coefficient. So if you were to factor this, this is, if we were to think about our strategies that you learned back in the day, you would say, okay, what numbers multiply to -30 but add to -7? So what you're really doing is taking all the factors of 30 and dividing it by all the factors of 1. So 30 over 1, 15 over 1, so I mean, you don't need to write the 1 there. 10 over 1, 6, 5, 3, and 1. I'm not missing anything, right? No. So those would be all the potential factors that we would try, or all the potential zeros that we would try when we factor this. So when we have these larger polynomials, the same thing works. So if I have this, again, we can't factor by grouping. There's nothing else I see that I can do. So I can at least have an idea of what the possible rational zeros could be. There's my p is 6. My q is 2. So all the factors of 6, everything that multiplies to 6, we could do plus or minus 6, plus or minus 3, plus or minus 2, plus or minus 1. Those are all my factors of 6. Q, we just have 2, right? Plus or minus 2 and plus or minus 1. Those are the two things that multiply into a 2. So those are all my factors of the constant. Those are all my factors of the leading coefficient. So the actual rational zeros are all the p's divided by the q's. So these are the things that we know could potentially be factors of this, be zeros of this polynomial. So I'm just going to go down the list. And actually, I kind of wish I wrote it the other way. I'm going to start small. So we have 1 divided by 1, so p over q. So we could have plus or minus 1. I could do 2 divided by 1. Which is 2, could be a 0, or plus or minus 2. I do 3 divided by 1. So plus or minus 3 could be a 0 of this polynomial. I do 6 divided by 1. So you can see I'm just kind of going through a pattern. I'm doing 1 over 1, 2 over 1, 3 over 1, 6 over 1. Now I can do it with the q value of 2. So 1 over 2. So 1/2 could be a 0 of this polynomial. So I'm doing 1 over 2. 2 over 2, that's actually already on there, right? 3 over 2, that's not on there yet. So 3/2, plus or minus 3/2 could be a 0 of this polynomial. 6 over 2, that one's already on there. So now I know what the possible zeros of this polynomial could be. So the 2 steps, I can figure out how many positive and negative real roots there are. And then I can actually narrow it down to figure out what those possible zeros could be. So I'm going to pause again. I would like you to try. Why don't you try the third example here, right here? Save us some space, and then we'll see how you're doing. Okay, so hopefully you knew what to do. If not, there's my work. And again, you'll notice that a lot of them start to repeat. So the 3/2 and the 6/4 are the same. The 1/2 and the 2/4 are the same. So here's all the possible rational zeros for this last polynomial here. That's a lot, right? If we take all those and there's a plus or minus for every one of them. So that's a lot to try. But that's where Descartes' rule comes into play. We kind of have an idea of how many positives there could be and how many negatives there could be. So the rational zeros theorem gives you all the possible zeros. Not all of them are necessarily actual zeros. So how do we determine which of the factors are actually zeros? We use the remainders theorem. So we do this synthetic, well, I wrote it below, but we use this synthetic division process that we've been looking at earlier. All right, so here's what we're going to pick up on next class. We'll do this as our bell ringer. Given this polynomial that we've already worked with, we're going to think about what the positive and negative possible number of real roots are. We're going to determine what the possible rational roots are. So those are our first 2 steps. And then we're going to go into this third step using synthetic division to determine what the roots actually are. So we're kind of narrowing it down a little bit at a time. All right, so let me know if you have questions, and I will see you guys in class. Bye.